And one of the other things, we will also have presentation material and files available on that web page, which is shown at the screen. This will include all the presentations, the files, as well as supplemental material that will help you later on if you decide to come back to any of these demonstrations on your own time. You'll be able to follow through the directions and set them up at a later date. This is the workshop agenda. Today is going to be fairly heavy on PowerPoints. We will give an introduction to GenCade. It will be basically just a brief introduction that will give you some more information about what GenCade is, what types of applications you can use it for, and then a little bit on model theory. I don't want to get too heavy on model theory since this is an introductory workshop, but I'll talk about that a little bit. I also discuss some of the workflow as well as the input and output files. Then I'll go over GenCade and the SMS. This is going to be a presentation that will show a simple example really from start to finish. So you'll get a better understanding of how you start out a GenCade application, how you'll develop each of your structures, how you will go through model control, how you will run GenCade, and then how you can view the results afterwards. The next bullet point is help on the web. I do have a presentation. I'm not going to go through that presentation, but what I will do is I'm going to go through and show you where on the SERP webpage you can find information about GenCade, where you can find information about some of the technical reports we've recently written, as well as some information about our GenCade wiki on the SERP wiki. We also are going to go through GenCade applications. I have 5 applications I want to discuss. These are going to be very different applications. Some will look at certain types of applications with GenCade. For example, one of those is Onslow Bay in North Carolina. This was a project we worked on for a very long time, and it's a more complex example, and we are looking at transport rates as well as shoreline change there, while in some of the other cases we were looking at actual alternatives. Then we'll go through a completed project demo. The reason I want to bring this one up is because you may have a situation where you didn't work on the project, but you're working with someone who has finished a project and they want you to take a look at the results. So this will give you a better overview to GenCade and the SMS. You can go through and see how you would actually make changes to their files. You'd be able to view input and output files, and then we'll also view some results. If we have some time at the end of today, and I'm not sure if we will, we'll go over a simple GenCade case. This is going to be very simple. It's just a straight shoreline with one groin and one idleized wave gauge. This example will be helpful because it will show you some basic elements of how to set up your GenCade grid. We'll also make some changes to the groin as well as the wave direction so you can see how you can make those changes. Going into day 2, we also do a couple additional demos. The first one is an example in Onslow Bay, North Carolina. We're going to look specifically at inlets, dredging, and beach fills. So this will be one side of GenCade. After we finish that demonstration, we will start our third demonstration, which I'm considering the structures in GenCade demo. This one is going to be actually a more of an overall GenCade demo. Although I am specializing in the structures, we also want to talk about inlets, dredging, beach fills, wave gauges, everything else that you're going to do in GenCade. This one will go into the third day. And then once that demo is complete, we're also going to go through some of the future capabilities of GenCade. This will just take maybe 5 or 10 minutes. I do want to mention we have released version 1 of GenCade, so these are future capabilities in GenCade version 2, which we are going to hope will be ready next year at some point. And then lastly, Rusty is going to give a presentation and a demo on a wave conversion tool, how that associates with GenCade. That's one of our future capabilities, so that will be where we finish on day 3. So this is some of our contact information. If you've just gotten onto the webinar, my name again is Ashley Fry. I am a research civil engineer here. I have been working on the GenCade development team for the past 3 years. We also have Rusty and Tanya available for questions. And then at the bottom of the screen is just some more information about our SERP website and then our SERP wiki page. That will lead you directly to GenCade. I should mention, as I said before, we do have our files and our demonstrations as well as supplemental material will be on the same page that you registered for this course. I don't think it's on there yet, but it will be on as soon as we can get it ready. So I'm going to go ahead and get started with an introduction to GenCade. And as I said before, this is really going to give a brief overview of what GenCade is, how you would use it, and how it came about. Then we're going to go through the background and overview as well as the conceptual coverage. I should mention here that we have two coverages in GenCade. We have the conceptual coverage, which is in real-world coordinates. This is the coverage where you can input aerial photographs, shorelines, wave gauge information, as well as any of your structure information. Once all of that is set up in GenCade, then you would convert to your 1D grid. This is where you would actually have grid spacing, so your structure would be referred to as cell numbers instead of XY coordinates. Then we're going to go over some GenCade capabilities, as well as some limitations and assumptions. Because GenCade is a 1D model, there will be some assumptions. Then I want to go through the workflow, as well as a brief model theory and formulation. So this will just be a brief background of our just the transport equations and our basic equations there. Then I'm going to briefly talk about the input and output files and then some of the cards. So to start out, how did we come about with GenCade? It came from Genesis and Cascade, which are two models that were developed. Genesis is an older model, Cascade was a newer model. Cascade, as you can see on the left of your screen, is a top-to-bottom model. It's used as a planning tool for RSM support. So what that means is we're looking at different projects on a more regional scale. Based on that, we want to have a typical grid resolution that's larger, about 500 meters on average, because we're looking at large-scale regional events. We're not as concerned about localized events. We have a time scale of months to centuries. We're also interested in multiple inlets, shoals, barrier islands. We also are interested in cumulative impacts, as well as retaining the curvature of the regional geomorphology. One thing about Cascade is because we have a larger typical grid resolution, it is a very fast model to run. On the other side, we have Genesis. This is more of an engineering design tool. It can represent all of the engineering details such as structures. We're interested in more local events, things that are happening on a local scale. So this would be interesting for engineering details and different alternatives. So our typical grid resolution is on the order of 25 meters. One of the things about Genesis is if you haven't used it, you've at least heard of it, but many people have used Genesis. It's a mature technology and there's big payback by updating. So our idea was to add the Cascade capabilities to Genesis to automatically include all of the Genesis features. So that might sound like it's very simple. We can just add the two codes together and we'll be able to output GenCade. Well, it was not that simple. It took us several years to get all these, to get this code correct, make sure everything was working, and to get all of our bugs out. So once we had that done with GenCade, one of the things I do want to mention is that with GenCade, we are saying that it is Genesis plus Cascade, but in order not to promise that we can look at regional scales on the order of several states in length, I would feel more comfortable saying that GenCade is Genesis plus inlets, which is the capability of Cascade. So some of the things that GenCade does, it integrates from planning through engineering design. and it can cover timescales from about 1 year to multiple decades. We are preserving the regional trends. We're also furnishing regional consistent boundary conditions to local projects and representing cumulative local projects interacting regionally. From Cascade, we're representing the inlet bypassing and tidal delta evolution. We're also resolving the engineered elements. One of the great things about GenCade is that you can include variable grid resolution for increased accuracy and efficiency. One of the things that's nice about this is if you have a grid on the order of maybe 50 miles and you're concerned about one particular area where you want more detail, instead of having that small cell size over the entire grid, so maybe you're looking at a 30-foot cell size, you would only need to have it in the area of added interest, and then you could have a larger cell size in other regions. This increases the efficiency of the model. It's much quicker to run. And then one of the last things we've done is improve the computational efficiency over Genesis. This has been something in version 1, which is what I'm going to be discussing over the next couple of days. We have seen some computational efficiency over Genesis. In addition, we've also been working on a version 1, release 3. This one has added computational efficiency even over version 1, release 1. One of the things about the version 1, release 3 is when you get in the SMS and you use that license code that I provided you, you'll be able to go into the models, and version 1, release 3 is the one that's available there. It's almost identical to release 1, which I'll be showing this week. We had a bug that was fixed with T-head groins that is fixed in release 3, and it also has an adaptive time step, but that is involved with advanced cards, so I'm not even going to discuss that in this presentation. And then again, adding Cascade capabilities to Genesis to automatically include all of the Genesis features. So I just want to briefly go through some of the conceptual processes that you'll find in GenCade. First, GenCade is a longshore transport and shoreline change model, so you can see those on the screen. From Cascade, we also have inlets involved. So as you can see the ebb shoal, the flood shoal, as well as the jetties, and then the bypassing around the inlet. In addition to those capabilities, I do have a few on here. Well, first of all, we do have coastal structures, which you can see here with this groin, but we do have some capabilities listed on here that we are working on for version 2. One of those would be grain size, so this D50 here. In this case, we're looking at 2 grain sizes, where it's 0.27 to the west of the inlet and 0.38 to the east of the inlet. That's something we're working on in version 2. Right now, we only have the capability to have a single grain size for the entire grid. Additionally, we've been working on cross-shore transport. This has been a study, and it's been work outside of GenCade. In the next couple of months, we're going to be incorporating that code into GenCade, and we're hoping to have that available in version 3. So with cross-shore transport, we're also considering overwash, windblown sand, and dune erosion. I want to go over a couple of the GenCade applications. So although we don't want to look at large-scale events, we can look at regional processes. We can also look at project planning and design. I'm mentioning regional sediment management here because GenCade has been funded by both the SERP, the Coastal Inlets Research Program, as well as the Regional Sediment Management Program. So we have beach fills, inlet bypassing, channel maintenance. The last thing I do want to briefly touch on is the intuitive interface. This is something we are very pleased about. We're working in the SMS, and it's very user-friendly. That was one of the biggest complaints about Genesis, is that it's a great model, it works, but it's not very intuitive. It's not very simple to use if you're a first-time user. So what's great about the SMS, and it is in 11.1, and we're so thankful that 11.1 has been released in beta form so that all of you can actually start using SMS 11.1 and using GenCade within it. It's so user-friendly that I'm thinking that in the next couple days after I go through all these demos, you'll probably be a little tired by it. It's very repetitive, but it's very simple, and it's something that you can come back to in about a week, and you should be able to get it up and working and get your grid set up. So I want to go through some of the model functionality and capabilities. First, I've already mentioned variable resolution grids as well as inlet bypassing. We have the Inlet Reservoir Model for calculation of shoal and inlet feature sediment balance. This is a more there is an Inlet Reservoir Model standalone. This is a more simplified version of that model. We also, as I said before, have the representation of the regional morphologic trends. In addition, we have the capability to have multiple wave input forcing locations. We do have that opportunity to introduce almost as many wave gauges as you could ever need. These wave inputs can come in any format. They can be in shore normal convention, meteorologic, oceanographic, or Cartesian. GenCade will recognize all of them and then convert to shore normal for the model. We have the representation of coastal structures, including groins, jetties, seawalls, breakwaters. I have T-head groins listed here. While we don't have that considered a specific feature in GenCade, we can create a T-head groin by a breakwater and a groin. So you would have to input these separately and then define them separately. But this will be read into GenCade as a T-head groin. We have the calculation of salients and tombolos behind breakwaters, as well as time-dependent detached breakwater transmission. With our breakwaters, we have two options. We can have a constant transmission as well as time-dependent transmission. So in that case, you'd have the opportunity to enter based on Aaron's or Seabrook and Hall, and you would have additional parameters that you would need to enter at that point. And then we also have the efficient calculation of breaking wave properties in the internal wave model. We have a number of GenCade assumptions just because GenCade is a 1D model. One of the first is that the beach profile maintains a constant average shape. So this is a general assumption apart from times of extreme changes as produced by coastal storms. What this means is that a steep beach is going to remain steep, and a gently sloping beach is going to remain gently sloping in a comparative sense and in the long term. One of the things about this is that although seasonal changes in wave climate can cause the shoreline position to move seaward and landward, with the corresponding change in shape and average slope of the profile, the deviation from the average beach slope over the total active profile is small. The second assumption is that longshore transport occurs only between the top of the berm and the depth of closure. So this is our active transport. This restricts the profile movement between these limits, and this is the simplest way to specify the perimeter of the beach cross-sectional area, which changes in volume from the shoreline can be computed. The third is that sand transported alongshore by breaking waves is not affected by nearshore current patterns. And then the last is that there's a long-term trend in shoreline evolution. This implies that the wave action producing longshore transport and boundary conditions are the major factors controlling long-term beach change. So I'm going to go through the general workflow of what you would do to start setting up GenCade. First, you have your coastal problem, where you'll formulate your question, you'll identify your constraints, and then you'll develop the criteria to review and evaluate your solutions. At that time, you'll probably start assembling and analyzing relevant input data. For GenCade, you can have a large amount of data available. For example, you would have shorelines, you would have wave information, you could have aerial photographs, you may have inlets that have dredging events as well as all of your shoal volumes, beach fills, and structures. After this, you would most likely develop engineering solutions and alternatives if your project requires that. Then you would develop and execute GenCade to optimize project solutions and alternatives. You would calibrate, validate, and evaluate alternatives. And then after that, you would evaluate your results. And you can do this either through the SMS or post-process outside in either Excel or MATLAB. This is just almost rehashing the last slide, but it gives you a little bit more detail about what we do in each of these steps. So again, we would compile our project data. We would assimilate all this data in GenCade with forcing and boundary condition input. And as I said before, we are going to do all of this in the conceptual model from our input data. So the conceptual model, again, is where we have XY coordinates. It's real world. So you can input an aerial photograph if you so choose. And one of the nice things about that is if you have a reliable aerial photograph, if you know that you have a groin at a certain location, you can just draw the arc representing the groin directly on top of that aerial photograph in the conceptual model. Once all this is complete, then you can convert to your 1D grid. And then that's where you develop your project grid. And then you can also develop different alternatives. During your simulation, you can execute calibration simulations, and you can do a number of sensitivity tests. We can also review and analyze the calibration results. At this point, we may need to refine our setups. This would be our model setups, so we may alter our K1 and our K2, which are our calibration coefficients. At this point, it's also a possibility that you developed your inlet or whatever structure you're looking at in the conceptual model, but when you convert to your 1D grid based on the cell sizes, your location may not be exactly where you want it, so you can refine that setup there. We can also execute production simulations. And then during post-processing, we can review the results, and we can also analyze and post-process the results. So again, here's a listing of the types of inputs you could enter into GenCade. You can develop, based on this, you have your pre-process inputs. You're developing your GenCade grid as well. It can be a regular or an irregular grid spacing. You're going to develop your initial shoreline. And this can either be brought in as a shapefile, as a coastline file, which is a CST. This is how the SMS reads these files. Or you can bring in a points file. Then, in some cases, you might develop a regional contour. This is how you maintain the desired overall shape of a curvature even if the model is run for a long time. So in some cases, if we do not have a regional contour, over time, the shoreline will eventually evolve to a straight line. But if you have a regional contour, this is where the shoreline will eventually evolve to the shape of the regional contour. For a regional contour, you can choose a number of things to represent your regional contour. One of those would be an average of several shorelines over time. You can choose one shoreline as representative, or you can choose an offshore bathymetry, going through your bathymetry, an offshore contour. We can assign wave inputs, multiple wave inputs. We can also supply the input control parameters. We'll input all of our structures or coastal projects, go through the inlets, shoals, and dredging events, and then also enter our beach fill events. And then the simulation outputs, we're going to have a number of GenCade solution files that come out after the GenCade simulation is complete. Most of these can actually be input back into the SMS so we can view them very quickly. Another one, which is the print file, is something that you can open and use the information within it to use for, if you're working within Excel or MATLAB, you can use those results to make charts. And then another is the post-processing. So once you input your solution files and your measured data, you can get your transport rates as well as shoreline change. With those transport rates, we can actually do sediment budgets. One of the things we're working on in version 2 of GenCade is creating these output files from GenCade that can be used as direct input into SBAS. That's the Sediment Budget Analysis System. We can also look at the results from the inlet bypass and shoal evolution. One of the things that I like to do with GenCade is comparing the measured results for that final year of your simulation to your calculated results. You can bring both of these directly into GenCade and can view almost immediately, and you can tell if you are having some issue with the model, or maybe you've put in the wrong value for something. You'll be able to tell that right away if your measured values are very different from your calculated GenCade values. And then you can also compare a number of alternatives. With post-process outputs, then we can have calculations, figures, images, and exported data. Within the SMS, there are figures, although they are most likely not going to be of the report quality you would want, but you can tell very quickly how they look, and then you can always go into Excel or MATLAB or whatever type of software you choose to develop those graphs. So I briefly want to go into the model formulation. This is our governing equation for GenCade, and it's formulated by the conservation of sand volume. If we look at the bottom of the screen, we have our distance alongshore, which is x, and then our distance offshore, which is y. That denotes our shoreline position. We also have d sub b and d sub c. This is our berm height, and this is our depth of closure. So you can determine your total volume change based on those values. So the change in x, the change in y, and then your berm height plus depth of closure, so your active profile. One of the things that we need to assume is that the beach profile translates seaward or shoreward along a section of coast. And then what we also can see here on the right is that the change in the volume is determined by the net amount of sand that enters or exits the section, which would be a cell in this case. If we have a difference in the longshore transport rate, which is Q, at the lateral sides of the cell, then the volume will change. This is our sediment transport rates. The first term in this equation is from the classical Cirque equation for calculating longshore sediment transport. A1 and A2 are our non-dimensional parameters, and then later Genesis later extended this part, this second term. It accounts for longshore current and associated transport induced by a gradient in the wave height. Some of the other things that you can see here is A1 and A2 include K1 and K2. These are sand transport calibration coefficients, and these are used as input in model control of GenCade. So here you can see K1 is the primary empirical transport coefficient. This affects the entire model domain, and it controls the magnitude of the longshore transport rate. On the other hand, we have K2. This is our secondary empirical transport coefficient. This only affects the evolution in areas influenced by wave diffraction near structures. So this is more localized. And then I briefly want to talk about the inlet reservoir model. As you can see in this case, we do have longshore transport moving from left to right in this example. So as we move into the inlet area, what is going to happen is some of that, some will move into the ebb shoal. Some of the transport will actually move into the channel and into the flood shoal. This is all based on the ebb shoal, how full it is in comparison to equilibrium. Also, some of the transport will move to the bypassing bar, eventually to the attachment bar, and then we'll have Q out moving down drift. And you can see the number of equations that show the flux of sediment into and out of each of these elements here. This is a listing of the output file format for GenCade. So I'm going to go through each one of these separately, and the first one is the instantaneous net transport. This is our QTR file. And the way it's formatted is that we have each time step recorded in GenCade. And for each of those time steps, we're going to have a net sediment transport for each of our cells. So if we have 1,000 cells, we're going to have 1,000 net sediment transports for each of our recording time steps. We also have our mean net transport, our left transport, and our right transport over the simulation or specified time. What this is actually showing is if you open up these MQN, MQL, and MQR files, what you'll see is you will have the sediment transport for each cell averaged for each year. So if you have 10 years in the simulation, you're going to have 10 rows. Each one will show each year. And then at the very bottom, you're going to have another row that's going to have the net sediment transport for each cell over the entire simulation. So we have that also for left-directed transport and right-directed transport. In addition to that, we have the shoreline position at the output time file. This is the .slo file, and this is actually one of what I consider one of the most informative files. If you open it up, you're not going to be able to tell much about it. It's actually going to show the Y position of the shoreline at each of our cells. So you're going to have a very large number. This is actually the offset from your grid at each cell. So based on that, you can look at it and you probably won't have a very good idea of what that means. But you can bring this file into the SMS and it will show during each time step where the shoreline is. So you'll actually be able to view it and compare it to measured values as well as your initial shoreline. We also have a calculated offshore contour, which is in the same format as the shoreline position output time file. And then we also have the inlet shoal volume output file. This is the .irv file. This one actually shows that at each time step, you can see how the ebb shoal, flood shoal, left, or the bypassing and attachment bar on the left and the right, how they change over time. So how they maybe are depleted or how they start returning to equilibrium. You can also open this kind of a file in the SMS, and I will show you that probably tomorrow. This is a listing of our GenCade input cards, and I don't really want to go into each of these, but I do want to give you an idea of what we have available here. The first couple of these show the paths and the name of the shoreline files. We also have the wave information as well as the path and name of our printed output file. This location is where we have information about our grid. So you'll have your X origin, your Y origin, and your azimuth. You'll also have a listing of the number of cells as well as either the cell resolution or a -1 indicating variable resolution. You'll have information about your model controls. So this is where you would have your starting date and your end date, as well as your time steps. You would also enter K1 and K2. Again, these are your longshore sediment transport coefficients. If we go to the other side of the screen, we have the option to modify the waves. So if we find that our wave, once we run GenCade, we're not seeing what we think we need to see based on the waves, we can change the angle, offset, or amplify the angle or the height. We also have the grain size, the average berm height, and the depth of closure. The grain size is always going to be in millimeters, regardless of if you're using feet or meters. I should also mention here that that is going to be the same way for your wave events. When you enter your depth of your wave, it's always going to be with your waves. When you enter your wave height, it's always going to be in meters, regardless of what type of projection you're using. And then these last several, all of these are related to our boundary conditions. GenCade has 3 boundary conditions: the pinned boundary condition, which is the default, moving boundary condition, and then a gated boundary condition. We also have a few other options for the moving boundary condition. We can specify as moving during the simulation period, the day, or for a time step. So if we consider a time step, this value is going to be extremely small because your time step might be 3 hours and you might have a simulation over a few years. And then the last couple things I just want to show you are just some examples. And this shows the variable grid along shore. In this first example, we have 200 cells. We also have a cell size that's constant at 10 meters. Now we can do the same type of a thing, but in this case, we're looking at a cell size that's variable between 10 meters in the lee of the breakwater up to 100 meters where it's not going to be affected as much by this breakwater. So you can see that the results are very similar, but you might think that this doesn't make that much difference. It's not going to speed up the model. It's not necessary. It might not in this case because we're only looking at a couple hundred cells. But when you have thousands of cells over maybe a 50-mile grid, this will make a lot of difference and it will save you a lot of time. And then lastly, I just want to briefly talk about transmissive breakwaters. In this example, we have a cell size of 10 meters and we have 200 cells. In this case, we have our KT, which is our transmission coefficient. And this is going to vary between 0 and 0.8. So in this case, you can see that when our KT is 0, we actually have Tombola formulation. However, when we have KT of 0.8, the shoreline is unaffected except right here, right behind the breakwater. So this is our information. Again, we have the SERP webpage as well as the wiki page available here. We are going to have all of these presentations on the website as soon as we can, so you'll be able to view them later. And with that, I think I'm going to go into the next presentation, which is an introduction to GenCade in the SMS. This one is going to give you an overview of the conceptual model, which I'd mentioned before. Again, this is where you set up everything in real-world coordinates. So this is where you would set up your shorelines, your waves, structures. Everything will be done in the conceptual model for your setup. Then once you convert to your 1D grid, all of your features are going to be referenced to grid cells. The GenCade input files will be created after you save GenCade. And you have a number of input files. These include your initial shoreline file. This also includes, if you have variable cell size, you'll have another file for that. You'll have a couple files for your wave gauges. You'll have one for each of those wave gauges. And then you'll also create your .gen file. This is your control file. And this is all the information from GenCade will go into that file to run GenCade. You also set up your model control, which is all the additional details about your simulation. You can run GenCade in the GenCade model in the SMS and then also view some of these results. So I'm going to start from the very beginning. So this is going to be step by step. This should start giving you a better idea of, in the last presentation, the things that I talked about. We are going to be going through a couple of demonstrations over the next couple of days, so you'll see this in more detail and actually see me do it, and I won't be, it should be easier for you to understand once you're actually seeing why we do things. But this should start giving you an idea of what we do in GenCade. So in this case, I've already opened up SMS 11.1. And I do have, this is SMS 11.1 development. Yours will not be development since it's been released, but we haven't made any changes to GenCade in the SMS for quite some time, so it will look identical. So the first thing you're going to do after you open SMS is you want to define that your map data is GenCade. So you're going to right-click on your default coverage. You're going to have this menu pop up here. We'll go down to Type, we'll click on Models, and then we're going to check GenCade. What will happen once you do that is this toolbar here will actually change so that we'll have the capabilities of GenCade and we'll be able to create all of our feature arcs and things of that nature, our grids and everything else. Next, what you're going to do is you need to define the location of your executable. You will only need to do this once, and it will be the first time you set up a GenCade grid. Once you've set this up once, the SMS will know where this location is, so they'll be able to find the GenCade model. If you neglect to do this before you run GenCade, then you're going to notice that you'll get an error that it has no idea where it is or what we want to run. So first, you'll go Edit to Preferences. Once you go to Preferences, you're going to get the SMS Preferences window to open. If you click on this File Locations tab, you're going to scroll down under Model to GenCade, and it's going to be near the bottom of the screen. Under Executable, the first time you use this, it will say Browse here, but I already have it defined on my computer, so that's why I have a program there. So in this case, the executable is version 1, release 1. Yours will actually be different. It's going to be GenCade version 1, release 3. And you'll find that under models of SMS 11.1 because it's been included with the SMS download. Then you'll click OK. The next thing you want to do is define your projection, because remember with GenCade, you can have a projection either in metric or in US customary units. So we're going to go Edit to Projection, and the current projection window is going to open. In the simple case that I'll do tomorrow, it's just going to be a straight shoreline. That we're just going to use a local projection, US survey feet. However, for most of these cases, you're actually doing real applications, so you need to have a global projection, especially if you need to bring in any aerial photographs or any shorelines. So you would click on Global Projection here. Then you would go to Set Projection, and this window is going to pop up. The projection you would define here. In this case, I'm defining it as UTM. You would go ahead and list your zone, your datum, the planar units, and then you would click OK. Once that's done, you can start bringing in your aerial photographs as well as your shorelines. In this case, I have already brought in my initial shoreline for this case. As you can see, it's a black line. This is because the SMS does not know what type of a line this is. It's just assuming it's a generic arc. Well, what we want to do is actually click on this. This is the Select Feature Arc button. Once we click on that, we can either double-click on the line or click once and go to Attributes. That's going to open the GenCade Arc Attributes window. Under Arc Options, we're going to change from Generic to Initial Shoreline, and then click OK. Then the line's actually going to turn green. The next thing we want to do is, say in our case, we're interested in a regional contour. One of the things we need to do is enter the regional contour in a separate coverage than your initial shoreline. And the reason we need to do that is because if we enter both of these in the same coverage, it's highly likely that both the initial shoreline and the regional contour will intersect at several locations along your shore. When that happens and you enter them both in the same coverage, we're going to have nodes that form at each of those locations. So this will actually split your arcs into multiple arcs. The best way to accommodate this is to open up a new coverage, and then you'll merge them later and they will be unaffected by that. So we're going to first go to Map Data. We're going to right-click on Map Data and go to New Coverage. This window is going to open up, and we're going to go to Coverage Type, and we're going to click GenCade. Under Coverage Name, I usually name it as some identifying feature. So in this case, I'm going to name it Regional Contour. And then I'm going to click OK. So now we're looking at the regional contour here in this coverage. We're going to do the same thing as before, and this is where it's going to start getting a little repetitive, but I think that's going to make you remember what we're doing more so. We're going to click again on Select Feature Arc. Then we're going to double click on the line, and then again we're going to open up the GenCade Arc attributes. And in this time we're going to click on Regional Contour, and we're going to click OK. Then what we're going to do is we're going to go ahead and merge the coverages. This is done by clicking on both the initial shoreline and the regional contour coverages. In order to click them both at the same time, you need to click on Control. This will allow you to highlight both, and then right-click, and we're going to go to Merge Coverages. This window is going to pop up, and it's going to ask, do you want to delete the coverages used to make the merge coverage? I usually say no, just because I like to have the other coverages available if I want to go back to them at any point in time. So now this shows what the merge coverage looks like. You can see both the initial shoreline in the green and the regional contour in this blue. The next thing that you may need to do is convert to a new projection. And one of the reasons you may need to do this is, for example, your shorelines are in a different projection than your images. So if we want to go ahead and do that, or say we want to convert from feet to meters, we want to use that projection. What we'll first go ahead and do is go click on Merge Coverage, again right click on it, and go to Reproject. We'll get this window popping up that says this is a non-reversible command and will permanently change the data. Continue. You'll click Yes. Then the Reproject object window will open, and we're going to click on Set. This first current projection should be the projection you're already using. Now under New Projection, you're going to add all of the new set projection. So in this case, I'm looking at State Plane Coordinate System as opposed to UTM. Your vertical projection should be in the same units as your current projection, which is in your horizontal. So this is meters, this is meters. I'm using state plane in feet, so the vertical is going to change to feet. We also need to change the projection of SMS, because right now we've only changed the projection of that particular coverage. So again, we're going to go to Edit Projection, and the current projection window will open. We'll click on Global Projection and go to Set Projection again, and you're going to change it from UTM to State Plane, and then we'll click OK. So now that we have all the shorelines and we have the projection set, we want to start adding our different features, and we're going to start with inlets. So the first thing we want to do to create an inlet is click on this button. It's the Create Feature Arc button, and you're just going to draw an arc from one side of the inlet to the other. I like to make these as close to the shorelines as possible. And the reason for that is because if you have a grid that is shaped slightly different from your orientation at the inlet, you may have an offset slightly, which means that an additional cell might be considered part of your inlet that may not be. So I try to make it as close to the points on either side of the inlet. Then we're going to go and click on Select Feature Arc, and again we're going to open the arc options, and this time we're going to click on Inlet. Inlet has additional attributes, so I'm going to click on Attributes and open up the Inlets, Reservoir Model, and Jetties window. We're going to go to Name the Inlet, and we'll click Galveston. We're going to go to under Volume, another window is going to open, and this is going to list your ebb, flood, left bypass, left attachment, right bypass, right attachment, and then your initial and equilibrium shoal volumes for each one of those. We also have the options for dredging. This is where you're going to input your beginning date, your end date, whatever shoal, so whichever one of these shoals to be mined, as well as your volume. Now we can enter jetties, and the best way to define your jetties is, in GenCade, they're defined as left jetty and right jetty. So you're probably wondering what that actually means. Well, the best way to think about that is, say you're on some type of a boat in the inlet and we're looking out to sea. So I'm sitting here, I'm looking out in this direction. the left jetty would be to my left, and the right jetty would be to my right. So in this case, this jetty that's to the north is the left jetty. So what we'll go ahead and do is we're going to actually draw these jetties as well. You may notice that we do have, it looks like we do have this node here. We do not, they're not intersecting at all. But if they were to intersect, there is a way to change that to a vertex so that we do not have an intersection of, or a division of one of your arcs. But we'll go ahead, we've already drawn the inlet, or the jetty. Then we're going to go ahead and select this arc again, using the same select feature arc that we've used before. We're going to open up the arc options and go to left jetty on inlet and go to attributes. Under attributes, this is where you would define your permeability. You would choose whether it's diffracting, and then you'd enter your seaward depth. You would do the same thing for your right jetty, but I'm not showing that because it looks exactly the same. Another thing that we can do is enter a seawall. So a seawall is always going to be, it's going to be landward of your shoreline most likely. What we have here is we would create it in the same way. You have to be careful for this because usually the seawall is going to be very close to your shoreline, just landward of it. So additionally, in a lot of cases, seawalls extend a large distance. So for this case, you'll probably need to create several feature arcs, and then you'll need to connect them over time. Then we're going to go to the Select Feature Arc. We're going to click on it, go back to the Arc Attributes menu, click on Seawall, and then click OK since we have no additional attributes for Seawall. We can also do the same type of thing for groins. So in this case, we're going to draw the groins offshore. One thing you can do with groins is you don't need to extend the groin all the way to the shoreline. We can extend it to here, and that would make sure that we do not intersect any of our other arcs, because we just need to know the farthest distance offshore. So we would actually have the length of the groin. So we would go ahead, we would create the feature arc, we would go again to Select Feature Arc, open the GenCade Arc Attributes window again, go to Groin, click on Attributes, and then you may remember this looks identical to the Jetties window. So we would input our permeability, go to diffracting, and go to seaward depth. We can do the same type of thing for beach fill. And again, it does not matter if you make your beach fill landward or seaward. It's going to be defined to certain cells. And based on what you input, then you'll have the inputs for the added width for that beach fill. So we're going to create the beach fill, and then we're going to select the beach fill again, click on it, open the GenCade Arc Attributes window, go to Beach Fill Event, and click on Attributes. Here's where we would list the beginning date, the end date, as well as the added berm width. In GenCade, we need to enter as the added berm width. You'll probably have your beach fills and volumes, but you can determine your added berm width based on the alongshore distance as well as your berm height and depth of closure. And then lastly, we have the detached breakwater. So you will draw that at the specified distance offshore. You would create it, as you can see. We're going to select it now. And then we have the breakwater defined under GenCade Arc Attributes. We're going to go to Attributes, and you can see a couple different things. We have Depth 1 and Depth 2. Depth 1 is going to be furthest to the left, like your left jetty, and Depth 2 is going to be like your right jetty. So we're looking landward out to sea. Depth 1 would be to your left, and Depth 2 would be to your right. We have a couple of different options for transmission. We have constant, where you can enter the permeability. We also have additional options such as errands and Seabrook and Hall. Instead of having permeability, where in this case we just have the default of 0, we'll have the option to have attributes. Another window is going to pop up, and those additional parameters necessary to solve those equations will be available. And then for a detached breakwater, it's going to turn orange. Now I want to go into the grid setup because I did mention that we had the left jetty, which is the north jetty. I do want to talk a little bit about what that means. So in this case, we have the shoreline here. And you can see that the grid is set up inland of that. In this case, we are going to start at this point to the farthest northeast and draw the grid from there all the way to the southwest. Now, why are we doing that? What we need to consider is, for this example, we want to consider walking down the grid to determine where it should be in relation to our shoreline. So if we walk down from this northern part to the southern part, the shoreline will always be to the left of your grid. So another example would be, in this case, you can see from north to south. If we were going from here, starting at the south, and going north, from south to north, your shoreline will be on your left, so the shoreline will be here instead. So we'll talk about that a little bit more over the next couple days when we go through some of these actual demonstrations. Once we've developed the grid setup, which is done by clicking on this button, which is your Create 1D Grid button, we're going to select the Select 1D Grid button, and then we're going to click on this square at the center of the grid. We'll continue on and open the Grid Frame Properties window. This is where we can enter the origin and orientation. The origin X and origin Y refer to our first point on the grid, so that in this case is going to be the northeastern point. We can also enter our angle. When we go into tomorrow, I'll discuss this in more detail, but the angle referred to under grid frame properties is actually different than the azimuth, which is referred to in GenCade, unless the angle is equal to the azimuth at 225 degrees. And the reason we have this, I'll discuss it more tomorrow, but this is just telling you your angle of your grid right now. The azimuth is actually how we're going to determine our shore normal if we were developing that on our own and not in the SMS. We also have eye size. That's the distance of our grid. So for this case, I'm looking at eye cell options, and we're going to define the cell sizes. In this case, I'm just looking at a constant cell size, so I would change the cell size to 300 feet. Once I change that number, the number of cells are going to change accordingly. We also have an option to use refine points, and I'll show you that a little bit later. And I click OK. So this would develop our grid. We would convert to 1D grid here if we have wave gauges that uses shore normal, because what we're looking at with GenCade right now is if you have your wave information in shore normal convention, SMS has no idea what your grid is if you haven't set it up yet. So we can't enter shore normal convention until after the grid is set. So we've set up the grid now. We need to convert to 1D grid very quickly, just in the case of shore normal convention. Then we can return to the conceptual model, which is here, and that's done by clicking on the Merge Coverage in the Map Data menu. To add the wave information, the wave gauge, you would go ahead and click on the Create Feature Point button, and you would draw your point wherever it's located. You can also do a single point projection under Edit. If you know an X and Y coordinate, you can just add it there. Or if it's in a different projection than your current projection, you can do that as well. So we're going to go and look at the Select Feature Point, and this will open up the Refine Point window. So this is the same window you would use to refine your points. So this is the variable grid resolution as well as the wave gauge option menu. If for some reason you were doing a refine point, this is how you would do it. You would check the refine grid in the I direction, and we would list your base cell size. It could be 30 feet, maybe in this case. And then you would click OK. But what we're looking at is a wave gauge. So we're going to check wave gauge. We're going to go to Options. The wave gauges window will open. We'll go to Depth. We're going to say that the depth is 50 feet. We'll go to Data. And this is where you can enter your convention, either shore normal, oceanographic, meteorologic, or Cartesian. We can enter this wave information in two ways. The first is just by copying it and pasting. We can also import it from a text file. I like to do that because it's easier for me than copying and pasting. It seems to be a little bit quicker as well. Once that information is within the wave events file, we're going to click OK. The last thing we want to do is convert to a 1D grid. And this is done by right-clicking on Merge Coverage. We'll go to Convert, and we'll click on Map to 1D Grid. This will open up the Map to 1D Grid file. And here, this is exactly the same as the Grid Frame Properties window. So maybe in this case, I've included refine points, so I want to make a change here. You can do that. Usually this will be the same as your grid frame properties. But say I've decided to use refine points, and I've set up the refine points. I've listed the base cell size there. Here's where I would click Use Refine Points. I would list the maximum cell size, and then I would list my maximum bias. What this means is in this case it's 1.1. So this means that for each cell adjacent to the smallest cells, we're increasing the cell size by 10% until we increase it all the way to 500, the maximum cell size of 500. We can either choose to use intergrowth or not. What this means is, for example, you have a groin field and you have 2 points on either side of the groin field representing your refined points. Most likely you would not want to have any varying grid cell size between the groins. You want to have that constant at a smaller cell size. So in this case, we're going to not check Use Intergrowth. But if it didn't matter to us, we could grow inside of 2 refined points. We would check the Use Intergrowth. So we go ahead and click OK. And now we've entered the GenCade model. So you'll see on the left side of your screen, now we have GenCade data and a GenCade grid here. I've unchecked the conceptual model, so now all you're going to be able to see is the GenCade model. So in this case, I did have refined points here, which you can see that it's a smaller cell size. You can also see your grids, or your jetties located here, and the inlet. We can see the seawall in blue, the groins located here, and then you can also see the wave gauge has been translated to the grid, and it has a cell location there. One of the things that you can do in GenCade is you can click on the GenCade menu. This will come up once you've started working with GenCade. And you see all these different options to edit. Usually I don't make any edits in the GenCade menu because I find it easier to make that change in the conceptual model. Because I work off the conceptual model for everything, if I make separate alternatives there, then I can convert to the GenCade model and I'd have everything saved. If for some reason I decided to make an edit here, say I wanted to make my alternative in the GenCade model, it wouldn't hold true in the conceptual model, and I might forget that I made that change and not know what alternative I'm actually working with. So the only thing I usually do here is make very minor changes. So one example would be for inlets. I might want to adjust the location of my bars because right now in GenCade, the default for the bars next to the inlet is adjacent to the inlet. And I may know that my attachment bar is further to the west of an inlet. So I might want to change that there. That's really the only thing I change in this menu. But here's where you would do your model control. So I'm going to scroll down to model control, click on that, and I'm going to go to GenCade model control. The first tab is Model Setup. So we're going to go to Computational Time. This is where we can list our start date, our end date, the time step, and the recording time step. We can also look at the beach fill, or we can also look at the beach setup. This is your sand and beach data. So this is your effective grain size, average berm height, closure depth, as well as your longshore sand transport calibration coefficients. We can go to our seaward boundary condition. One of the things that you might want to do here is list the number of cells in your offshore contour smoothing window. This is iSmooth, and this is almost like another calibration, another way you can calibrate. In this case, actually, 50 would be incorrect. It would actually move it to 51 since it must be an odd positive number. What iSmooth means is if we have a larger iSmooth, that will result in an offshore contour that has less curvature. So it will be more smooth. iSmooth of 1, this is I guess this would be considered the most radical of any of the iSmooths. This would result in an offshore contour that's parallel to the shoreline. So you can sort of tell what the differences are. If we have a larger iSmooth, we're going to smooth the shoreline more than if we have a smaller value. And the default in GenCade is 11, but you can change this value as you need to based on what you want. And then lateral boundary conditions. As I said before, we have the left and the right lateral boundary. We have pinned, we have moving, and we have gated boundary conditions. So in this case, I'm looking at the right lateral boundary condition as moving. We can go ahead and specify the shoreline displacement velocity. It can be positive or negative, and it can be for simulation period, time step, or a day. If we had a gated boundary condition, we could go to the length of the groin from the shoreline to the seaward tip. Once this is all done, it would be best to save everything multiple times, but if you haven't already, you would go ahead and save now. Then you would go to GenCade and you would click Run GenCade. It will run for a couple minutes to maybe 10-15 minutes. It usually is very quick to run GenCade. There are a couple of situations that take longer, particularly if you have a lot of breakwaters with diffracting tips, but usually it is fairly quick, no more than about 20 minutes to run GenCade. So now we can view the GenCade results. And in this case, we're looking at, under GenCade Grid, I've brought in the .slo file. So now we can look at the shoreline change, the rate of change, and the shoreline. You can also change under time steps so that you have these different time steps here. So I'm looking at the last time step in my simulation. So I can compare the shoreline, which is the calculated shoreline, which is the red with the blue, to the green. So you can see how this compares to the initial, or you could even bring in other shorelines to compare it to something, maybe your 2000 shoreline. Another option is you can go to Display and Plot Wizard. And under Plot Wizard, we can go to GenCade Shoreline, and we can click Next. Here, we can go ahead and check the last specified time step, and then click Finish. So now we can look at the shoreline and see very quickly what it looks like, and we can make some decisions on if we want to go ahead and do all the work to set up and post-process outside of the SMS, or we can find something, maybe you see some type of instability somewhere, or we notice we're not seeing the trend that we would expect. We could go back and make our changes before looking at the results outside of the SMS. And then we can also go to Plot Wizard and do the same thing and go to GenCade Inlet TS. We can click Next, and then this pulls from the .irv file, which is our inlet shoal volume file. So you would specify your inlet, go and list your start time and your end time, and then you can click any of those different functions. So you could list your ebb, flood, right bypass, whatever you're interested in looking at, and click Finish. So in this case, I've selected my ebb shoal. And you can see over time, we did have a dredging event, and that the shoal is starting to return back to equilibrium over time. So that presentation should give you a better idea of what you would see in GenCade in the SMS. The next thing that I'm going to go through is I want to go through some of the applications that we've covered recently. So you can see a better understanding of what types of applications you can use GenCade for and what we've already done. Each one of these is somewhat different, and I see it's already after 2:15, so I'm going to try to go through this one fairly quickly so we can go through the conceptual model for Matagorda at the end. So as I said before, we have 5 cases that I'm going to discuss. I'm going to talk about Point Lookout, New York. Then I'm going to talk about Onslow Bay, St. Johns County in Florida, Sargent Beach, and Matagorda Peninsula in Texas. And the last 2 were actually from one project, but we had 2 separate grids for alternatives, so I'm going to talk about those separately. So the first case I'm going to look at is Point Lookout in New York. And you can see the study area here. This is Point Lookout, this is Jones Inlet, and we have a couple groins in this region here. We want to see how different alternatives would affect the shoreline in the area over 50 years. This shows the model setup. The initial shoreline is actually that orange shoreline on the screen. The modeled shoreline is the red with the blue representing your bars. You can see your wave gauges that are back on the grid, as well as your beach fills, which are showing your cell numbers. You can also see the groins as well as the jetty here. One of the things that was done was they modified the wave input to account for shoaling and sheltering, which you can see here based on the transport, mean net transport. This could be another example of what Rusty's going to talk about on Thursday with the wave conversion tool. And then this is a listing of the areas of reoccurring nourishment in this region here. And this shows the shoreline change rate in feet per year. In this area, it's up to almost 25 feet per year. So the first results are a comparison between the calculated results and the 1994 shoreline. So the 1994 shoreline is the orange, and the modeled is the red and the blue. So you can see that the results look fairly consistent with the measured shoreline. We can go further to the west. This is that groin field here, and you can see again our results are fairly consistent. And then this is a zoomed in view of those couple of groins as well as the jetty. So we looked at a couple of different alternatives. The first shows the existing condition with no action after 15 years. And in this case, you can see that the shoreline has eroded significantly compared to the initial. We actually, in this location here, we're predicting that we're going to see enough erosion to actually affect these houses in that region. This shows the existing condition with the recurring nourishment. So this is a nourishment of an added berm width of 110 feet, recurring every 5 years. So you can see how much improved this particular case is, or we have the advance of the shoreline compared to the initial case. We can also look at a couple structural alternatives. In this first case, we're looking at 2 additional groins just to the west of the 2 groins that we already have. In this case, we still have that 110 added berm width for the beach fill. And then on the right, we have 4 additional groins, and you can see how the results look comparatively. So to go through the results, 1, the no action case is not feasible. We noticed that the 2 additional groins had the greatest effect on shoreline position, and we didn't see much difference between full length, which are shown here, and a shortened groin. We also had 4 grinds show greater shoreline accretion across Hempstead Beach, which is to the west of Point Lookout, and that provides long-term stability for the erosional hotspot. And then reoccurring nourishments are critical to the project's success. Long-term stability of shoreline at the erosional hotspot can be mitigated with frequent nourishments. Structures spanning the erosional area were modeled and found to increase accretion at the shoreline, suggesting structures will best mitigate shoreline control. And that GenCade was successful in evaluating long-term effects to the shoreline for the 50-year planning period. The next case is Onslow Bay in North Carolina, and as you'll see the map, this is a very complex case. This is something we worked on for a couple years. It was one of our first projects, actually. How this project was one of the reasons we came about to getting to work with GenCade. It was very complex, as I said, and this was helpful for us because we were able to find some of the bugs more quickly because we threw GenCade to this very difficult case, and we found a lot of these bugs or issues more quickly than we would if we would have just been testing very simple idolized cases. So although it took a while, it was helpful for us, and we think it's going to improve GenCade in the long run. So for this case, we used GenCade to improve the understanding of the regional sediment system and also to provide information for a sediment budget. I have a couple pictures on the screen from a site visit we did in Onslow Bay. So the first picture on the right shows Bogue Banks near Bogue Inlet. This is in the northeastern section of Onslow Bay. And what you'll notice here is that near this inlet, we had severe erosion when we visited, to the point that these houses needed to be protected by sandbags. We also have a couple of structures in the area. North Carolina does have a ban on hard structures, but there are some exceptions to that, like Fort Fisher, which protects a historical site. This is in the further southwest section of Onslow Bay. And then also we have a north weir jetty at Masonboro Inlet, as well as a south jetty there too. So this is just an overview of Onslow Bay. It's more than 100 miles long. You can see the curvature, so that made this project very difficult to begin with. We had 11 inlets, and we also had varying barrier islands. So we had several developed barrier islands. We also had some that were undeveloped, and then Onslow Beach is used for military activity. For example, Bogue Banks is very developed, so we had a lot of information there. We had a lot of beach fill events. Also, Beaufort Inlet near Bogue Banks, this is dredged very frequently. It's a deep draft navigation channel, so we did have a lot of good information about Beaufort Inlet. As we move further to the south, we have a couple islands here, Bear Island and Browns Island, that are undeveloped. But as we move to the south, closer to the islands that are near Wilmington, these are large tourist areas. They also have a lot of homes on them and are very developed. So these areas, we do see a lot of activity. We have a lot of beach fills. We have a lot of inlet dredging that renourishes those beach fills, and we do have some structures in that area, including the Carolina Beach Seawall. So this goes through our procedure, and you'll probably see the first thing on the screen is that we have 3 grids. And to go over that briefly, there are 2 main reasons why we had to go with 3 separate grids. The main reason is because of the amount of curvature of Onslow Bay. In this case, we have more than a 40, almost, in this case, if we extended the primary grid, we'd almost have a 90-degree angle between the shoreline and the primary grid. If we have an angle greater than 45 degrees between the grid and the shoreline, we're going to have instabilities. So it's best not to increase your angle between those more than 45 degrees. Additionally, if we considered extending this grid, at one point you will actually have multiple shorelines in one cell. GenCade would be extremely confused by it, and it most likely would not run. So we went with 3 separate grids. These grids are working together. The way they work is that each of these grids overlaps the other grid by at least one inlet and one wave gauge, and they're at least several miles in the overlap area. Some of the standard inputs is because this is a more regional study. We're not as concerned about smaller cell sizes near certain types of locations. So we have a grid spacing of 300 feet. We also have the shorelines from 1997 and 2004. These were used for a validation period. We used the 1980 to 1999 WIS wave data, and this was also used for our long-term 20-year transport study. So we looked at transports over those 20 years. We had a grain size of 0.17, a berm height of 4.5, and a closure depth of 26.5. You can see the calibration coefficients, K1 and K2. Those were 0.6 and 0.4. And then we had a validation period, I said already, and we used composite wave data because we didn't have WIS wave information between 2000 and 2004. We chose the dates within the WIS wave between 1980 and 1999 that were most similar to the 2000 to 2004 years. So I'm going to go through the grid setup for each of these. I'm going to start with the secondary east grid. This one includes Beaufort Inlet and Bogue Inlet. And at Beaufort Inlet, we do have a lot of information. We needed to develop the 1997 initial shoal volume. This was estimated by subtracting the yearly shoal volume calculated by Olson Associates from the volume of the 2004 survey. We also used beach fill volumes, as you can see here, and then we had the added berm width. Additionally, we used yearly maintenance dredging records, and then we decided to split the volumes into the east and west bypassing bars. So 70% went into the west bypassing bar and 30% went into the east bypassing bar. And our yearly average of dredging was about 1.1 million cubic yards. To go over some more details about Beaufort Inlet, one of the things you'll see is that the estimated shoal volume decreased in about 100 years by over 20 million cubic yards. We also had the channel depth increasing from 15 feet in 1900 to being dredged to 47 feet since 1994. And then, as you saw in the previous slide, the yearly average maintenance dredging was about 1 million cubic yards. Until 1997, this was all disposed in this offshore disposal area. But now we actually have a nearshore placement site where material has been deposited since then. This is a really great survey that we have because this shows us a better estimate of where our bypassing and attachment bars and our ebb shoal proper are located. Based on this and our entire shoal volume, we can determine what the volume is for each of our different morphologic features. So we can determine our attachment bars, our bypassing bars, and our ebb shoal proper. We can go to our primary grid setup. This one was actually one of the more difficult ones to set up because this stretch of coast had almost no data. We had 7 inlets. We had to consider them all at equilibrium just because we couldn't find enough information for initial and equilibrium volumes. We included 3 beach fills on Bogue banks. We also used a gated boundary condition at the Masonboro North Jetty, which you can see here in the blue. And we did have dredging at Rich Inlet. That's shown at the bottom of the screen here. And we do have those 4 wave gauges. This one overlaps with this first grid, and then this one overlaps with our southern grid, or our southwestern grid. Additionally, Bogue Inlet is on both of these grids, and then Rich and Masonboro are on both of these grids. If we go to our secondary west grid setup, you might notice that this one is actually a very complex case. We may only have 4 inlets, but what is happening in this area is more complex. For example, we have several structural events. We have the Fort Fisher revetment, which I mentioned, which is located here. We have the Carolina Beach seawall here. And then we have Masonboro Inlet, which is the only inlet with structures, with jetties, in the entire Onslow Bay area. Additionally, these are the areas that have the most development on the islands. So we have a lot of nourishment activity and renourishment activity on intervals, as you can see here. We also have a lot of activity at the inlets where we have a lot of volume dredged almost every year. And on a lot of these cases, this material is actually being used to go back on our beaches. So we have a lot that is going on in this particular grid. So I'm going to go through each of the grids. This one is a secondary east grid. And what we have here is the blue is the measured shoreline change, and the red is the calculated shoreline change. We're particularly happy with the results at Beaufort Inlet because this almost exactly matches the measured results. And this is where we spent most of our time, and we had the most details about this inlet. We also did statistics for our results. We looked at our Breyer skill score, the root mean square error, and the bias, as well as the correlation coefficient. In addition to that, we have our left and our right bypassing bar evolution, and we compared it to the 2004 survey at Beaufort Inlet. So in this case, what you can see is that we do have a lot of dredging events. So our left and right bypassing bar is being depleted over time. And we do see the correct trend because in 2004 it is depleted from the 1997, although we are slightly overestimating that. If we go to the primary grid, you can see both the measured and the calculated in the blue and then the red. And again, we are fairly happy with these results. We've spent a lot of time on them. If we look at the rich inlet ebb shoal volume, you can see that over time we did have 3 dredging events, and the ebb shoal was depleted slightly, but we are starting to return back to equilibrium. And then the last of the 3 grids is the secondary west grid. Here we have the measured in blue and the calculated in red. So this is actually one of the more difficult ones just because of all the activities in the area. We had so many beach fills, so many dredging events, as well as several structures in the area. So this was somewhat more difficult for us to do our validation and calibration. And then this one was actually, we had the highest correlation coefficient of 0.84. If we go ahead and look at the mean transport, this is from 1980 to 1999, so that's our 20-year case. And what you'll notice here is the black is the net transport. So overall, this is very low. It's less than about 200,000 cubic yards per year. And you can see in the southern half, we're actually moving the sediment in the southwesterly direction, and in the north, it's actually more to the northeasterly direction. You'll also notice we do have a convergent nodal point at Beaufort Inlet. Additionally, we can look at the gross transport, and over the entire stretch of Onslow Bay, the gross transport is about 1 million cubic yards per year. We were happy with this because this is very similar to some of the literature that we found that stated that the gross transport in the Wrightsville Beach and Carolina Beach area, which is all in this region here, is about 1 million to 1.1 million cubic yards per year. So the summary of Onslow Bay is that the goodness of fit of the calculated shoreline ranges from 0.31 to 0.71, with correlation coefficients between 0.7 and 0.84. Then we also have the results from the 20-year simulation. The gross mean sand transport was on the order of 1 million cubic yards per year. Net transport was small, usually under 200,000 cubic yards per year, and it was directed to the northeast from New River Inlet to Beaufort Inlet and to the southwest for the southern half of the bay. The results also indicate that Beaufort Inlet is a convergent nodal point. This means that the net sand transport is into the shoal on both sides of the inlet. So this means that the dredging of the shoal should have a minimal net impact to the adjacent beach. One of the next cases is St. Johns County in Florida. And this was a large-scale study. It included much more than just the GenCade work, but I'm just going to talk about GenCade on this study. So the first thing is, what is the optimum placement dredging volume and interval, and the beach placement volume and interval that will supply adequate sand to maintain the 2 shore protection projects in St. Johns County? So how can we use GenCade to help us answer? We want to use GenCade to give us an idea of the volumetric limit that can be mined from the ebb shoal at St. Augustine Inlet in its present condition, which does not cause a significant long-term effect on morphology and the volumetric recovery of the shoal. And then we also want to know how much sediment and what nourishment interval is required to maintain the present volume of the active and planned shore protection projects. This shows the GenCade setup, and this spans all of St. Johns County. This picture is zoomed in around St. Augustine Inlet, so you can see multiple wave gauges. We have an input of shorelines from 1986 and 1999. We also have dredging and placement information as well as structures. The model is also calibrated, and it was dependent on the equilibrium shoal volumes, the inlet bypassing rates and locations, the regional contour, as well as how interpolation occurred between the waves based on the stationing of those waves. This shows some of the ebb tidal delta volume change, and what we have here is Villano Beach, Anastasia State Park, and then the St. Augustine Beach Nourishment Project. So what I want to tell you a little bit is we have all these alternatives, so I'm going to briefly discuss what they mean. Alt 1 looked at a dredging volume of 1 million cubic yards every 5 years, and then that was placed on the beach at that same interval. Alt 2 included 1.35 every 5 years of dredging and beach placement. Alt 3 was 2 million cubic yards every 7 years, and that same beach placement was used. And then Alt A4 was 3 million cubic yards every 10 years, and the placement was the same. So you can see in this case that what we're looking at is Alt A1 is actually having an increase in the final ebb tidal volume. Alt A1 or Alt A2 and A3 had a decrease in the final volume, while A4 had a minimal increase. We also have Alt B1, B2, C1, and C2. Now these are similar. Alt B1 is dredging of 1.35 million cubic yards every 5 years. That beach placement was also put on the beach in one location. Whereas the other 3 cases, we moved to 2 locations at Villano Beach and at St. Augustine Beach. So B2, we have 1.65 million cubic yards that's dredged every 5 years, and a certain placement was placed on Villano Beach, and another part of the placement was put on St. Augustine. And in C1 and C2, we had 3 million cubic yards placed on the beaches every 10 years. Part of that is on Villano Beach, and part of that goes to St. Augustine Beach. Although we had the same placements, the amount, meaning the cubic yards per linear foot, were different at Villano Beach based on the distance alongshore. So this is just a listing of some of the alternatives. So these are actually the amount of placement on each of the beaches. So for B1, it's 70 cubic yards per linear foot every 5 years. And we continue that. So you can see the initial shoreline, the calculated shoreline, the inlet bypassing, and the regional contour. So this just gives you a better idea of what's happening in each case. And then this shows the volumetric results. So in this case, we're actually not looking at shoreline change like some of the other cases. We're looking at how the volumes change over time. So you'll see for A1 through A4, we do have a decrease at St. Augustine Beach, but in A1 and A4, we do have the volume increasing at the ebb tidal delta. All 4 of these do result in a decrease in the volume at Villano Beach. And then if we move to B1, B2, C1, and C2, you'll see that we have a decrease in St. Augustine Beach. We have an increase in the ebb tidal delta over 50 years for C1 and C2. Alt C1 and C2 are very similar except that C2 shows an increase in the volume at Vilano Beach. We don't really see that in C1, but we do see slightly more of an increase in the volume change at Anastasia State Park. And based on the results, they chose Alt C1 as the one that was best met the requirements of the study. And then the summary is just that GenCade was used to perform and estimate the certainty. It does not include all of the three-dimensional morphologic processes. They're not all in the model, but it can be applied to calculating future sediment budgets. The benefits of coordinating and modifying dredging intervals can be explored simultaneously with varying beach fills and volumes. And the greatest benefit lies in determining the optimum mobilization periods and coordinating regional effects to save in the mobilization and demobilization costs for dredging and beach placement. I'm going to continue on and talk about Sargent Beach and Matagorda Peninsula. This is one of our recent projects, and we're looking at two sections along the coast. The first one here is Sargent Beach, which has a revetment protecting the shoreline. And then we have, this is Matagorda Peninsula between 3 Mile Cut and the mouth of the Colorado River. I'm going to talk about both of these briefly and then just go into Sargent Beach. So we're going to start with the 1995 and 2000 shorelines. We have 4 wave gauges, and then we have the Sargent Beach revetment and the Mitchell's Cut and mouth of the Colorado River included. Matagorda Ship Channel is at the boundary, so it's not included within the model. Now we can look at the net transport, and here you can see that our GenCade values, which are the blue, are very similar to the values from the literature. If we move north of Mitchell's Cut, the values from the literature are slightly lower than the GenCade values, but as we move further north, the values from literature are a little bit larger than the GenCade calculated rates. We can also look at the 1995 to 2000 measured shoreline change. The measured is in the red and the blue is the calculated. And we were fairly pleased with these results. It was a difficult calibration. You may notice that south here, if you can see here, we do show in the model that we're calculating accretion, while the measured is actually seeing erosion. We weren't as concerned about that location because when we did our studies at Sargent Beach and Matagorda Peninsula, having any difference at that location did not affect the studies in those other alternatives at those areas. So I want to talk about Sargent Beach first. One of the things to keep in mind about Sargent Beach is this is one of the fastest eroding beaches in Texas. We had 2 phases of this study. The first was to determine the feasibility of structural solutions to reduce erosion. We wanted to protect the beach habitat, and we also wanted to protect the Gulf Intercoastal Waterway, because what we were noticing is already certain locations along the revetment at Sargent Beach are eroding so that it's being exposed to wave action. If we go 10 more years, a much larger section of the revetment may be exposed, and at some point the structure could be undermined. In Phase 2, we needed to refine our problem statement based on the sponsor's input. I'm going to talk about Phase 1, but I also want to talk about Phase 2. This included segmented breakwaters. We wanted to do an adaptive and scalable plan. We wanted to have minimal downdrift impacts. And then we also wanted to have multiple layouts to accommodate incremental funding. So here's a listing of all of our alternatives. We looked at beach fills. We also looked at a single groin, a groin field, as well as breakwaters. And you'll notice we did use a grid that was shorter than the grid for calibration. And the main reason we did that is because breakwater alternatives require a shorter grid because the computational time is so much longer than some of the other structures, just because of all the diffracting tips. Like in this final case, 81 breakwaters does take a long time to run. So we look at the no action case. And one thing that pops out is that about 6 miles of the shoreline recedes through revetment after 5 years with no action. And this entire section of coast, actually the entire grid, shows that there is going to be erosion over that 5-year period. We're also looking at the gross transport, which is basically constant at about 400,000 cubic yards per year. We go to Alt-1, which Alt-1 is 3 million cubic yards of beach fill over 10 years. That equates to a placement density of 57 cubic yards per linear foot, and that's also equals an added berm width of about 100 feet. What you can see in these results is that the beach fill does not increase the beach width. We do see a slight increase in some of these areas, but for the most part after 5 years, we don't see any effect. It keeps the shoreline the same as it was before. So this would require additional nourishments for it to be effective to protect the beach, but this is not a cost-effective option. Secondly, we can look at a single groin east of Mitchell's Cut. Alt-2 includes the beach fill from Alt-1. It also has an unrealistically long groin to demonstrate the maximum trapping capacity. Alt-2A just has a single groin. So what you'll notice here is that the groin has no impact north of about 57,000 feet. So what's happening is at 57,000 feet, Alt-2, the blue, is identical to Alt-1, which is the beach fill case. And in this chart, you'll see that Alt-2A, the single groin, becomes identical to this no action case. So we're not seeing any effect northeast of that point. If we continue on, we look at a groin field plus a beach fill. That includes 28 groins of 600 feet, spaced 1,800 feet apart. And then Alt-3A is a groin field only. So we're noticing that the groin field has little effect on the shoreline because for the most part, we're seeing that even with a groin field, it's almost identical to the no action case. We do see that there is some more protection at the northern end of the revetment, but we are seeing the recession to the revetment like the no action case. So now we get to breakwaters, which was chosen as the alternatives we wanted to pursue and continue studying. What we looked at was 10 breakwaters placed at 350 feet offshore. We looked at a couple different offshore distances, and based on those offshore distances, we looked at different depths. We also chose different breakwater lengths and gap sizes, but we decided to go with a breakwater length of 220 feet and a gap size of about 330 feet. If we continue on, you can see at the bottom of the screen, we have our Phase 1 with 350 feet offshore. And while we do have some Pomolo formulation, we do see that if you average how much the shoreline is where the breakwaters are located, we actually do have an increase in the net shoreline change over that 5-year period of time. Additionally, the gross transport is decreased to about 225,000 cubic yards per year. One of the studies we looked at in our literature review was Holly Beach in Louisiana. And one of the ways they decided if the project was successful, the criteria was that the gross transport was decreased by about 50%. So in this case, we're seeing close to that percentage of decrease in the gross transport. This is our Phase 2. We looked at 15 breakwaters placed at the same distance, the breakwaters were the same length, and the gap size was the same. So as you can see here, we have a similar, they look very similar to Phase 1, and you can see also that the gross transport is very similar as well. We have Alt-4, which is Phase 3. It's 81 breakwaters placed at 350 feet offshore. What we have here is the 81 breakwaters span across the entire revetment. And in this case, on the bottom right, you can see that we do have an increase in the shoreline change compared to the no action case. We do have this unusual activity here where at the revetment right here, we do have a lot of erosion where the revetment is not as close to the shoreline. This is because we do see a slight buildup of sediment at our first breakwater. That's something that we could change the size of the breakwater and the gap size to change that effect. Also, you may notice that to the south of the inlet, you're seeing a lot of erosion in that area. So we needed to develop a mitigation beach fill because we didn't want to impact anything outside of the project area. And since we're taking so much sediment and trapping it behind those breakwaters, we're not seeing that sediment move around the inlet. So we did need to consider a mitigation beach fill. And then just a summary, the best structural alternative at Sargent Beach is breakwaters. Multiple offshore distances and depths were tested with the breakwaters at Sargent Beach. Several phases were simulated for the selected Sargent Beach breakwater setup, and the mitigation beach fill necessary southwest of Mitchell's Cut for the Sargent Beach breakwaters. And then lastly, I want to talk about Matagorda Peninsula. This is the problem statement. It's been breached by ephemeral inlets in the past. We want to determine, again, the feasibility of the structural solutions to reduce erosion, similar to Sargent Beach. And these include protect the beach habitat, reduce the storm damage, and also reduce the sediment impoundment along the mouth of the Colorado River East Jetty. The jetty was built just a couple years ago now, so we don't have enough monitoring to even know the amount of bypassing that naturally occurs around the East Jetty. So that's another thing we needed to keep in mind. This problem statement was refined during Phase 2, and our sponsor wanted us to look at a groin field between 3 Mile Cut and mouth of the Colorado River. The goal was to widen the beach by up to 200 feet, and we also were asked to design the project so that it does not impact 3 Mile Cut. This shows the grid that we used for the Matagorda Peninsula alternatives. We looked at a 28-mile long grid that extended from 3.3 miles southwest of Mitchell's Cut to southwest of mouth of the Colorado River. We had 2 wave gauges. We did have a smaller cell size between 3 Mile Cut and mouth of the Colorado River, and we looked at 5 and 16-year-long simulations for this case. So I'm going to flip through each of our alternatives. We had our first alternative, which was no action, and then we had varying distances apart and varying groin lengths. So Alt 1 was 7 groins, the maximum length was 400 feet, and the maximum spacing was 800 feet. And you'll see as we move to the southwest, these become shorter and closer together. Alt 2 was 5 groins, the maximum length was 400 feet, and the maximum spacing was 1,200 feet. This is very similar to Alt 2. We have the same amount of groins, except these are a little bit longer at 600 feet. Alt 4 is 5 groins at 600 feet long and 1,800 foot spacing. And Alt 5 is 3 groins at 800 feet long and 1,600 foot spacing. And these were all constant at that length. And then this just shows a summary of all the different alternatives. We didn't include any beach fills. We included a permeability of 0.3 for the groins. I did include a 115,000 cubic yard per year mechanical bypassing around the mouth of the Colorado River. We do not know how much is occurring at this time, and we don't even know if there will be funding if we need to bypass around mouth of the Colorado River, but I use this just so we could choose which alternative we wanted to spend some more time on. So I'm going to flip through each of these scenarios. The red is Alt 0, the orange is Alt 1, the dark green is Alt 2, the light green is Alt 3, the blue is Alt 4, and then the light blue is Alt 5. So you'll probably notice a few things right away. And the first is that of all the alternatives, Alt 2 has the least effect. So we're seeing the least amount of shoreline advance and the least shoreline erosion to the downdrift side of the groins. And we also notice that Alts 3 and 5 are seeing the most effect. We chose Alt 5 as our scenario just because we're looking to the north of these groins, and this was the case that had the most shoreline change. So we wanted to look at additional variations of Alt 5. So the first thing you'll see, and this is comparing Alt 5 to the no action case, we do have a lot of shoreline change at 3 Mile Cut, and this was something that our sponsor didn't want us to have. So we thought, well, maybe we can move these groins to the southwest. So we shifted them approximately 1,600 feet to the southwest, like that. And then this is what the results look like now. We're actually seeing more shoreline advance to the north of the first groin, and we're seeing about the same amount of erosion to the south. This has helped improve the amount of shoreline change at 3 Mile Cut, so that was a good thing as well. We also wanted to look at a comparison, and in this case we wanted to compare to the no action to Alt 5 with no beach fills and no bypassing. So the first thing you're going to notice is without any bypassing, we actually have a buildup of sand to the northeast of the mouth of the Colorado River because we have no bypassing. And you can see to the south we do have a large amount of erosion. So you are seeing the effects of having the 3 groins. You're seeing the effect where we have the increased shoreline at the north groin, and we do see slight amounts of erosion compared to the no action case, but we still are not eroding from the initial condition. One of the things we also wanted to do, because we weren't sure about the amount of natural bypassing or if we would be able to have funding for mechanical bypassing, we wanted to compare what it would look like to have different types of beach fills and different amounts of bypassing. So you can see 2 of these charts. We have the dark green is no bypassing with no beach fill. The light green is no bypassing with a 200-foot wide beach fill. The dark blue is 200,000 cubic yards per year with no beach fill. And the light blue is 200,000 cubic yards with a 200-foot beach fill. So one of the first things you'll notice is that in the case where we don't have any bypassing, we do have this buildup of sediment all to the north of mouth of the Colorado River. And in the case where we have the beach fill, we actually do have the increase from the no action case in all areas. If we do have 200,000 cubic yards per year bypassing, to the south of this second groin, we do see erosion from the initial condition. This is all exaggerated in the 16-year scenario, where in the case that we don't have any bypassing, we build up almost 300 feet of shoreline at that east jetty. So that's something to consider as well. If we look to the south, we do have immense amounts of erosion here. Now in the case where we have 200,000 cubic yards per year, we have a lot of erosion to the north of the jetty, but we're seeing that we do have about 100 feet of shoreline change to the south of mouth of the Colorado River. So we looked at all these conditions because we are not sure what the sponsor will want. One of the things we did mention is that we need to have good monitoring for several years so we know more about what is happening at the inlet where we have the new jetty. But in this case, we wanted to bound the answers between having 0 to 200,000 cubic yards per year bypassing versus having no beach fill versus a 200-foot wide beach fill at the jetty, at the groins. So, and then this is the summary of the Matagorda Peninsula. Shifting the groin field to the southwest significantly improved the results. Of the 3 groin configurations modeled at Matagorda Peninsula, 3 groins of 800 feet spaced 1,600 feet apart produced the best results. And the rate of bypassing in the construction of a beach fill affects the shoreline change in the area. So it looks like we're actually at 3 o'clock, which is the time that our webinar is scheduled to be complete today. I ran a little bit over what I wanted to cover today. I also wanted to show you our website and show you where you can find the information. And I did want to start a conceptual case so you get a better idea of what you'll see in GenCade. Unfortunately, we're at the end of the day, so I'm not going to do that now. But when we start tomorrow, I'm going to go ahead and start out by showing you our website, showing you where everything associated with this webinar is located so you can access it. And then I'll briefly show you what the conceptual model looks like, show you how the results will look if somebody else did a case, and then I'll hopefully do that in the first 10 to 15 minutes. Then we'll start the simple example, which is the straight shoreline. We'll go through that case, and then we'll begin on the more complex Onslow Bay scenario with inlets, beach fills, and dredging. So I hope today was very informative for you, and I know I didn't give you a chance to really ask me any questions, and I know we're already at the end of the day. So I know that Tanya and Rusty have been answering questions as we've gone along. So I'm going to talk to them after the webinar is over, and if we see any questions that they haven't answered completely, I'll look at those and I'll start the session tomorrow by answering those. So I thank you for listening today and being attentive, and we will see you all back tomorrow. So I thank you for your time, everyone, and we'll see you tomorrow.